All right, I'm going to record this session as well. So, okay, well, so guys, so we worked really hard in the past 3 weeks. You know, whether it's about learning programming, learning machine learning, learning deep neural network, and or maybe sometimes you see your friend, your child, your enemy, right? Maybe they were so possessed in front of a computer and start labeling data. Have you seen that? Right, thousands of pictures. So you probably see it. You know what? Today we're going to show you our product. Maybe it works, maybe it doesn't. I don't know, right? But we're gonna see it. So also, I want to welcome two Yings. So we have Richard. Your wife looks like you're joining. Awesome, right? Hi, Ying. And also we have Ying Jiang. So she's a co-founder at the AI Camp. Also my wife as well. So welcome, welcome. Okay. So what are we gonna do? Okay, right now is we're gonna have maybe Team Rockfish take away the stage to essentially share with you your journey at AI Camp. Okay. I also forgot to introduce another one, Shan, who's also one of our instructors, Shan Berger. So thank you, Shan. Yeah. Okay. All right. So why don't we start with Team Rockfish? Go ahead. If you want to share a screen, you can share a screen. But right now it's share screen is enabled. So feel free to take away. Yeah.
I'll share the screen.
Okay. Ooh.
Okay. Hi, my name is Sergi, and I'm a part of Team Rockfish, along with Catherine, Raul, Madeline, and our instructor, Richard. We created this mask detector product, which detects whether or not someone's wearing a mask. Next slide. The reason why we created this product was because we wanted to create something that would benefit everyone globally and not just cater to a specific group, which creating a product influenced by COVID-19 kind of accomplishes that goal. Additionally, we wanted to aid businesses in enforcing and guaranteeing that proper safety guidelines are being followed. And lastly, this pandemic has affected everyone across the globe. We wanted to create this product in hopes to ensure that all customers are wearing masks as advised by CDC guidelines, which can result in a decrease in cases and a healthier environment for others.
Okay, next we're going to discuss how we made this product. So to make this product, we followed a basic schedule that had basic steps, which included determining our project, collecting and cleaning the data, labeling the data, training the model, testing the model, evaluating it, and then deploying it. And to do this, we used resources such as Labelbox to label our data. Our instructors also helped us with any issues we had, and they helped guide us through our project. We also used YOLO to help train and test our model, which is basically an object detection system, and other resources such as Google Colab and Flask. We also used our skills that we learned from AI Camp to help make this project. This includes the theory of concepts that include deep learning, supervised learning, convolutional neural networks. And this helped us understand what we were doing when making this product. We also learned Python coding, how to acquire data, train, evaluate, and other steps of this product. We also learned a very important lesson, which is using data to make decisions. So after testing our model, we used the data, the results of the model to make decisions and determine the accuracy, precision, and recall. And teamwork was also very big. We split the jobs up into per person, which helped us divide and conquer.
Mm-hmm.
Here are some challenges and stories we had. So top 3 challenges we had included, since given that this camp is only 3 weeks, we had a limited time to learn a lot about AI and apply it to build a fairly complicated product. There are also some issues with tools and environment. And we also faced some debugging issues while building project artifacts. Then some stories that we had throughout creating this product was that Raul's Zoom kept cutting out, which was probably really annoying for him. And the instructor sometimes forgot to allow the team to share their screen.
I thought that's mostly Zoom. Like, okay. I'm sure that's a joke, but
Okay, so now I'm going to do a live demo of the website. So basically, you can find our website here at rahulganesh123.pythonanywhere.com. And in our website, we have basically who we are, our motives, a timeline of the project, which basically showed all the steps that we took to achieve this idea. And also we have some pictures and resources. But now I'm going to show you how it actually works. So let's say I upload a random image. So basically the model will, since the model has already been trained, it can take this image and predict whether or not the person will have masks or no masks. So in this case, the person has no masks, but let's say I upload another one and it can say, this person has a mask. But there are sometimes, we have like a few errors that occur. Our model is not perfect. So for example, if I upload this picture, as you can see, the person in the middle, there's no label for her face, even though she has a mask. Or if I upload this person, there's 2 labels on his head, but there's only supposed to be 1. Mm-hmm. So in order to like summarize, our model does work in most of the cases, but there are a few cases where we need to retrain our model in order to make it more accurate. And before we go back to the presentation, I would like to invite maybe one of the parents to come in, maybe screen share and try out the model for themselves. And we just want to prove that it works for any pictures and not just preloaded pictures that we have. Mm-hmm. So if any parent wants to screen share and try it out.
Anyone want to volunteer?
Sure.
We don't mind doing it. We don't know how to screen share.
Oh, it's easy.
Oh, where is the screen share button? We're doing it. Content. Okay, share content. Oh, screen. It's pretty intuitive.
We can send the URL over the chat too.
Yeah, that would be easier, right?
Broadcast. Start broadcast.
What do we just do?
Are you using iPad? What are you using?
Yes, iPad.
Okay, that would be a little bit difficult.
Should we go to our computer?
Oh, it's
right,
okay.
well,
No. Using iPad is even better because you can take a photo of yourself. So we can. Okay, can Rahul send the picture maybe? I mean, send the link to the URL.
Yeah, I'll send the link right now.
Yeah.
Go get my computer.
In the big computer.
Okay, so the link. Oh, it's already sent. Okay.
You open it? With somebody else until we get it set up.
Okay. All right. So I guess we need another volunteer.
Yeah, I can do it.
All right.
See the screen?
Uh-huh.
Okay.
Yeah, we can see your screen.
All right.
So you can Google search a photo or something,
Yeah, let me do that.
Just to declare, I've already tried it with a photo of Michael's friend Eugene. For some reason that exists on my computer.
Did it work?
It works.
Okay.
Okay. Yeah, this is a good one. Let's try.
Oh. Okay, that's our leaders of the country.
Yeah, exactly. So let's try one with mask and one without mask.
Here we go.
I didn't do this on purpose, but
Way to go, Ganesh.
that's what's happening. All right, let's try it. Try our product. Okay, let's try the first one.
I think they're the identical picture, but just 4 pictures.
Oh, okay.
Oh, wow. Look at that.
Can I take a
Oh,
better
yeah.
look at the Nancy Pelosi? Oh yeah, it's
Wait, hold on. No. They're all yellow ones are the ones that has mask.
masks. So that's
Yeah.
yeah,
That really worked.
it works.
Shame on you, Trump.
That's awesome, guys.
Yeah,
It's so impressive.
that's impressive. Okay.
Excellent.
So by the way, that bug, you see like Mike Pencer, that 2 circles, that bug, I know how to fix it. Okay, anyway, that bug, I know how to fix it. We can always fix that later. That's nothing. We can fix it. Yeah.
Great. Awesome job.
Rahul, take away.
All right, I'm share my screen again.
Yeah.
Okay, so, all right.
Okay, so what's next? Well, the first step is to retrain the model. So as you guys have seen, it does a pretty good job, but there are still a few bugs and a few flukes, like you can see with this image right here. And that's mostly due to the fact that we trained it on only about like 2,500 labeled images. So a good way to visualize our model performance is called a confusion matrix. If you have never seen anything like it, pretty much on the left, you have the true labels, so what the label should be. And on the bottom, you have the predicted labels, so the label that the model spits out. And you can see here that it does match up most of the time, but not always. For example, 64 times, the label should have been face with mask, but the model put out a person not wearing a mask. So it's not perfect. The next step is to collect data, clean it, label it, and retrain the model. After that, it's time to deploy it in the stores. So we have to go talk to store owners, see if there's any demand, see if our product interests people. If so, we'll integrate a Raspberry Pi, add a camera, set that all up, and then start deploying locally in small local stores.
Mm-hmm.
If you guys have any questions about the model or the process, please feel free to ask.
So is there a % accuracy that you guys came up with that the model is good for, or is it not quantifiable?
So the confusion matrix also has the percentages. It's that other picture, Madeline.
Yeah, I can actually screen share that one if you guys want.
Yeah, do that.
Let me just go find it.
Or you could pull up the website. It also has it.
That's okay. I was just curious. And is that a function of how many pictures you put it through for the training?
Yes. So accuracy has to do directly with. Here, wait, let me just screen share. It has to do directly with the amount of pictures you have. Can you guys see my screen?
Yes.
Yeah. So this is the confusion matrix with the percentages.
Got it. Okay.
So with detecting face mask, it has a 0.79.
Oh.
And
is there a certain percentage that you would need to hit in order to productize it?
It sort of depends on what we're looking for. So to be able, because we want this to be, we want to get it out. We don't want it to be perfect because we want to have a product and then get feedback afterwards. So we'd maybe start with something a little bit better than this, but it doesn't have to be completely perfect before we start deploying it.
Okay,
I have a question. When you're trying to check for the mask on a picture, right? Are you trying to identify the face first and then see a mask on it, or is it just that you're just looking for a mask? What if I have a dummy on like a head. If I wear the mask and on my head, not on my face though.
I can answer that question if someone else wants to do it.
Okay, sure, you can do it.
Yeah, so it does detect faces with masks and faces without. That's how it detects, for example, when you put a picture of someone without wearing a mask, it still detects a face. So if it is wearing it incorrectly, the model will be confused because it doesn't see the mask around the area that it usually sees it. And so it will say that the person is not wearing a mask. Which,
No,
by the
what I
way,
meant was like if the mask is worn on the head, I mean, in the sense at the back of, instead of on your mouth and nose, you turn it around like 180 degrees and you take a picture of your head with a mask at the same level. Does it detect it as a face with mask or head with mask?
as in like you'd have a mask on your face and then you turn the picture 180 degrees?
No.
So I think I just want to jump in here. I think Madeline just said that if the model currently only takes masks worn at the correct position on the face as a yes with mask. I think that's what you said, right? Because it only has seen 2,000 plus examples, and I believe many of the examples are chosen not with like some, oh, we're just throwing some weird mask wearing pictures in there, like not that. That probably didn't happen. So I think the model has mostly seen like the correct mask wearing.
Which suits our purpose, because we're looking for, the goal of our product is to look for people wearing the mask correctly, because it's no help to anyone if you're wearing the mask on your ear or on your forehead or whatever. So
can you see my screen? So I was just curious about this question, and I googled this image where one person was wearing a mask not correctly and the other one was wearing incorrectly. And you can see the one that didn't wear it correctly, it just said face without mask. Right? So it does exactly what we wanted it to do.
Okay.
Right. So yeah.
That's
awesome.
Thank you.
Yeah, this is awesome. It actually performs better than I expected, to be honest. Yeah.
I got a question. So if you're going to deploy this in stores, most probably you want this to be operating in live video, right, rather than pictures. Mm-hmm. Any plans for or how to improve to get to there?
Yeah. So basically, like we know that we probably have to like retrain our model in some aspects, because when we actually tried like making a video of sorts using this model, and in some cases it came up with the incorrect answer. So we probably would have to retrain our model in order to acclimate to the video structure. But then after that, we could deploy it into stores.
I want to add also, when you sort of like predicting a video string, it's a little bit different from predicting frame by frame. Because in a video, you do have history of the time series. So each frame, they're linked to, like one another. But when you're predicting frame by frame, you're treating them independently. So we need to add a little bit more stuff in there, but I think this is, quite doable. Yeah.
Good, thank you.
Okay, more questions? These are great questions. These are great questions.
So was there thought put into the business model side of things on whether this is going to be a hardware product or a software only product that can run on any, security surveillance system?
As of right now, they're like, we didn't really think that much into the business side, but I would think that this would probably be like more of a software product, because stores they all already have camera systems put in place. So we just have to like, we already have the infrastructure. We would just need to implement that. So I think ours would be more of a software product.
I would agree. Good job.
Okay, so if there's no more questions, what we can do now is we can switch gear to Team Javas, okay? And maybe you guys can take away and presenting, what you did and what you learned so far. So yeah, go ahead.
I'll be the one sharing screen this time.
Okay.
Okay, can everybody see this?
Yep.
Okay. So welcome to our project. We call it a street sign detector. And basically what it does is just detect different street signs. Okay, so this time we'll be introducing ourselves. So my name is Alexander and I'm a student at LCM Montessori.
Hi, I'm Riley and I go to Amador Valley High School. And Sam, unfortunately, isn't here today, but she is part of our team and she goes to, I don't know.
Goes to Castellijo.
Yeah.
Okay. So, hi guys, my name is Siddhant and I go to St. Francis High School in Mountain View.
Mm-hmm.
I'm Kathy Tran. I go to Valley Christian in San Jose.
Mm-hmm.
And hi, I'm Shane, and I was the instructor on the team.
My name is Michael. You guys know me. I'm also instructor.
Since our model is called a street sign detector, it identifies traffic lights, stop signs, as well as crosswalk signs. We can train it to detect more traffic signals later, but we chose these due to their importance as well as the time constraints we had for constructing this model in 3 weeks. A practical application for our model is for the development of self-driving cars. So in order for self-driving cars to be more effective, they need to be able to follow traffic regulations. And in order to follow traffic regulations, they have to be able to identify traffic signals as well as traffic signs.
So for the practical application of this product, so self-driving cars are currently in development and they're slowly but steadily coming into our present day lives. Of course, they're going to be a staple of the future and we have to get ready. So these cars require a unique program that's able to identify traffic lights and signals. So in order for that to occur, we decided to develop a product that will be able to identify these signs and traffic lights, and so that these self-driving cars could follow traffic regulations and stay safe on the road. So for the production, we utilized multiple resources, including YOLO, which is an object detection software, Python Anywhere, a web hosting service, which allows us to deploy our code and website, Google Colab, which is a computer used for setting up YOLO and CUDA, NVIDIA CUDA, which is basically software that is used to interface with YOLO and allowing it to utilize the GPUs. Google Drive, which is a file storage solution, and Labelbox, a service used to label the images and data. So we have the full process on the next slide. So basically, the first thing we started with is collecting data. Obviously, we need to collect data in order to train the model. So right now, because of the time constraints, we only chose 5 things for our model to recognize. The three types of traffic lights, as well as stop signs and crosswalk signs. So we designated one type of sign or signal to each team member, and they collected masses of images and data of that sign or signal. And we put this into Labelbox and manually labeled each image for what they were. Like we identified it as a traffic light or a sign. Then we programmed the model and configured YOLO in Google Colab. And using this configured YOLO, we were able to set aside two groups of images, a group for training the model and a group for testing the model. So we trained the model using YOLO, and we also tested it to make sure it was as precise and accurate as possible. And lastly, we took all our scripts and deployed them into pythonanywhere.com, which allowed us to have a website that people could interface with, and was functional. So we will show you a demo of that soon, but for now, let's talk about the challenges we faced.
While building such a huge project over the course of 3 weeks, we ran into plenty of obstacles during the process. So in the first few days, we had to collect and label our pictures. However, one of our signs, the yellow light, is much harder to find than anything else because they only come on for a split second before turning red again, so it's much harder to photograph. And after we collected all our data, we had to get our model ready for training. However, we ran into quite a few issues because we all downloaded different things at the same time instead of going in order, which caused a lot of issues with our files. And setting up YOLO and our CUDA GPU was hectic because there were lots of errors with the versions and compatibility. And finally, to make our lives easier, we had to write some scripts to make our tasks more efficient, and that got a bit more frustrating at times because errors are popping up left and right. For each of the challenges we faced, we had to somehow find a way out of it, or else we're not gonna meet this deadline and get this project done. So although we didn't get 1,000 images for each sign, the model still trained pretty well and was able to detect our street signs. After running our code out of order and breaking everything, we restarted the process and made sure that our communication was clear. So only one person is running the code at a time and not interfering with the other person's process. By reorganizing code and using hardware accelerators of the GPU, we were able to optimize this process and make everything run faster. And lastly, we had a lot of help from our best friend, Google, for resources that helped us find our mistakes and solutions to overcome them.
Okay, so now I'll be demonstrating a live demo of our model. Okay, so this is the website. We have about, features that it can detect, and then our team introduction.
Mm-hmm.
So I'll be demoing a few images to give a general sense of how it works. So this is a stop sign image. And as you can see, it detects stop sign, and it also has that error where it detects multiple times.
Mm-hmm. We can solve those.
And then this one, it has two red lights and a crosswalk. And as you can see, it detected all three of them. Mm-hmm. And then this is the final example. This one, it's a little bit hard to see, but the blue are the yellow lights. The green one is the red light, and here's a green light. And it failed to detect this green light. And then for our confusion matrix and accuracy, as you can see over here along this diagonal, it detected red lights 81% of the time. It detected crosswalk signs 85% of the time, and yada, 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 with stop sign being the highest at 97% and yellow lights at the lowest at 0.71%.
And so yellow lights, you also would predict as red light, 14%.
Yeah, okay. And there's many, we evaluated the model using 900 test images, and this is just a summary of all of that. And as you can see, there's some times where there should have been no detection, but it still detected something where it shouldn't have been. So in this case, in that previous example where it detected multiple objects on the same stop sign, that would have been classified as no detection, but it still detected something. And then,
yeah, sorry, do you have do you guys have essentially like the percentage of the objects, or cases where you shouldn't detect anything over, you know, however many objects you have in this whole plot? Because you know, like this is all normalized across the row, right?
Yeah.
Yeah. But would it be nice to know, for example, in the no detection case, would it be like, you know, 3% of picture or something like that? Yeah.
Okay. Yeah, we didn't really think about that, so we don't have any information about that.
Okay.
And yeah, so of course, like there were errors on both sides, like issues on both sides, kind of. So some of the labels, maybe like we mislabeling some of the things. So then when the detector detected that, since we didn't label that there was something there, it was marked as an error. And other times, since we had 5 people labeling data individually, so some of our labeling styles were different. So some people might have labeled something differently. So that might have also contributed to some of the errors shown here. And back to the slides. Okay, so throughout these 3 weeks, we learned many things. And first of all, in the very beginning of camp, we learned Python. Python is a very simple yet powerful language, and it is used a lot in many machine learning stuff. And then after learning Python, we learned more advanced things, such as the library pandas and NumPy. And then through that, we learn how to manipulate data and efficiently and quickly. And then we also learn data visualization libraries such as Seaborn and Bokeh to create plots such as heat maps and histograms to visualize data such as COVID-19 data. And then we also learned about YOLO, the object detection system, and DarkNet. And we also learned the inner workings and how it worked. And other than that, we also learned many machine learning concepts, such as convolutional neural networks, how they work, fully connected layers, and other advanced concepts such as these. And then other than that, we also learned many things that don't exactly have relationship with machine learning, but are also valuable skills to know. For example, web design. We had a general introduction to front end and back end, and through that, we designed the website that you just saw. And then other than that, we also learned about making decisions with data, and that it's also very important to make connections where you can and to be confident in yourselves and to not stop when because you think you cannot do it.
So now for the outlook, where do we go from here in the future? So obviously we want to make sure our model can be expansive and cover more traffic signs and signals than just those 5, since there are many more on the road and the self-driving cars should be able to identify those. And we would also like to increase our accuracy by adding more images of the current signs and signals that we already identify our model, so that our model is more accurate and precise. And we need compatibility for videos, since the self-driving cars will be on the road and the camera needs to always be on. So it needs to be able to detect these signs and signals in real time so that it can make decisions quickly. And it needs to, we could work towards the implementation in self-driving cars itself. And as a prototype, we can maybe implement this in a Raspberry Pi with like a camera module, have it detect signs and signals in real time and check the accuracy and precision. Overall, like there are many ways we can improve this and actually make this a little bit more useful for the future. And yeah, thank you for listening to our presentation.
Awesome. So maybe we can stop sharing and have, you know, like people ask questions, like any questions you have.
I have a question kind of for both groups, kind of a general question.
Okay, one of the thoughts here is like for the signals, traffic signals detection, red, green, or the amber, right? So instead of,
so Dan, so could you hold for 1 second?
Sure.
Let's have David finish asking that question, and then we can have.
Sure, sorry.
Yeah, sorry about that. Yeah, David, could you go ahead, please?
Oh yeah, okay. I wasn't sure if anybody here could hear me. So looking at the performance of the two products, it seemed like the traffic signal prediction performance was slightly better with half the data or less. And the face recognition one was a little bit less, but it had more data. Is that because of the complexity of the data, or was there any general thoughts about that? I mean, both of them at 80% look really good for that amount of data, it seems.
I think there was kind of a misunderstanding. To evaluate the model, we used 900 images, but to train it, we used over 4,700-ish images.
Oh, so 900 was just for testing.
Yeah.
But to
Not to
train
mention, I
was
think
4,000. Okay.
I think you could also take into account that traffic signals don't change too much. I mean, they're pretty standard, and faces vary, an extraordinary amount.
Yes, I was wondering about that too. And can I ask, were these neural networks, the black box that you trained?
Sorry, can you repeat that question?
So what structure were you training? Was it a multi-layer neural network, or what was it?
Okay, so I understand it, we used a deep neural network that mainly consisted of one convolutional neural layer, and then after that, a fully connected layer. We used a YOLO object detection system, which is a lot faster than other region-based convolutional neural networks, and that has its special method to increase speed while also maintaining efficiency. And so, yeah.
Just want to add in there. So everything Alex said was correct, except there's one part where it's not just one common nets, it's actually multiple common nets to extract features. Yeah, but everything else is absolutely correct.
And how long did it take to train both products? So to run through the traffic signal 4,000 data images, how long did that take?
So for the traffic sign one, training took place for a long time, and it kind of varied depending on how fast the GPU speed that we were given on Colab. So sometimes it would be really fast, and sometimes it would be slower. But generally, it took a few days of just constantly running it for it to get to its current state.
Oh, a few days.
Yeah, actually what happened is, yeah, it took a long time since obviously we had so many images. And also because of that, we had two people doing it, training the model, Riley and Alex. Riley had originally started, but since there were so many images, he ran out of space. So Alex had to resume the training. So obviously it took a long time, but we were able to finish it this Tuesday, actually. So that was a relief for us.
Well
Wait,
done.
I didn't know you only finished this Tuesday. I thought you finished last week.
No, we finished the training this
Oh,
Tuesday.
so you gave us a model that sort of worked, and just on the background, you're still training it.
And how about for Team Rockfish? How long did the training take for the masked and unmasked images?
Yeah, so it also took us a day or two because we also had a decent amount of images to process through for the training model. So yeah, it took us a day or two to do. Yeah.
Can I ask what size the images were? 20 pixels?
I mean, it varied. Not every image had the same size. So I don't know. I guess you could look up the range, but I don't know.
Yeah. I want to make sure also so Nant, you had a question earlier, right?
Yeah, I did.
Yeah, what was your question?
Okay. The thing is, yes, this is about the traffic light, signal detection. So I guess this is only to detect if it was red, green, or something, right? In a traffic, as we have seen in different lanes, for example, there's a left turn lane. There's a traffic signal for that as well versus the ones that go straight are on the right. So there are different signals and there are different lights at a given point for each of those lanes. So as something to go forward with, how do you plan to say that your lane has a green versus the other beside you, which is a left turn lane, has a red?
I think that part is more of the logic of the self-driving car software itself, rather than the identification of the traffic light. Like, it needs to understand which lane it's on, as well as what's in front of it, right? So I think it's more of a logic of not identification, but other functionality that the car needs to learn. But yeah, the car can, or sorry, the product can detect every light or signal on the image, but knowing which lane it's on is a whole different requires whole different logic or a whole different program that this I'm not sure if this object covers yet, but we can look into that in the future.
Mm-hmm. Very good, very good. Other questions?
So as I understand it, you have to write a program or a code in order to, let's say, detect a face mask, right? And then you run the pictures through it to train it. And then do you have to go back and update the code to increase your efficiency? Is that the way it works? It's a general question for either team.
Sort of. So we were using a ConvNet and then a fully connected net, right? So in the fully connected net, you have a bunch of weights. And if you know what weights are, pretty much they just determine how much a certain characteristic influences the end result, which is what the model is going to predict. And so what it does is it goes through with the images, and it'll run an image through, and it'll get an output, and oftentimes the output isn't what it should be, and so it'll look at that and it'll determine what the difference is, what the loss is, and then it'll go back and back propagate, which is it'll go back and change the weights up, like, oh, this one needs to go up a little, this one needs to go down a little, and it continues through the whole net like that. And then so when you train again and again, your weights get closer and closer and closer to what they need to be.
Got it. Thank you.
That was a great explanation. That was a great one. Especially when you said propagate. That was like, that's the magic right there. Yeah. Okay. Anyone else have questions?
So yeah, I'm just curious. Did you guys look at the performance of how long it takes, especially in either case? Does it take a second or two, or does it take like 100 milliseconds, 10 milliseconds for you to come up with the result? I think that's pretty important. I'm just curious if you guys try to do that.
Our team did not specifically measure the amount of time it took for object detection, but I'm sure that's something we can do to improve our product. And from what we've seen so far, it does reloading the site and everything takes about a second, but I'm sure the time is much less than that because it involves multiple elements.
Mm-hmm.
So we have to look into that and try to improve the performance in the future.
Yeah, again, I don't know specifically, but if you look overall at YOLO, it takes around 2 seconds, maybe a little bit under.
Guys, do you remember what's the frame rate that YOLO can actually run at? Someone go to YOLO website, you can see it.
Is it 30?
Yeah, it can go more than 40 frames per second. But when you think about, for example, human kind of like perception, that's like 24 frames per second, right? So YOLO can run like way faster. And this is also hardware dependent, because you have a GPU, and then it's going to be way more efficient. Yeah. But if you, deploy that using Raspberry Pi, I think you can get to like maybe 5 frames per second, something like that.
Yeah, it's on the website. It says 30 frames per second.
Yeah. And also, the faster you go, of course, the accuracy will suffer. But yeah, that's the nature of the game. Yeah.
I'm wondering if
We can hear you.
Oh, I'm wondering if Team Rockfish has identified likely customers.
Likely customers?
Yeah, so we were thinking that like if we ever were to deploy this in the future, we would probably go into like maybe local businesses at first because they're struggling deeply because they're getting like, barely any customers, and since they're so small, that's driving a lot of them out of business. So we were thinking we would probably go to first like smaller local businesses to help them out, and then we might go to like larger chains.
Mm-hmm.
Very good.
Yeah, first just like, go to local businesses and just say, hey, this is a free product. Can we just put the hardware here and collect data, right? So you collect data first and maybe get their phone number. So someone came in without a mask, you send a text message, right? Get some feedback first, deploy to maybe 5 or 10 stores. And then once that is good, then you can talk to, more like bigger chains because you have data already, right? And maybe you can, charge a subscription fee, maybe $80, $100 per month or something, Yeah.
Yeah,
You need to have the permission of the people you're photographing, right?
In the store, you don't because that's your property. Okay. Okay, why don't we do this? I think this is great. This is actually the first time we're doing this presentation style. So thank you for coming. Thank you for supporting. And everyone here, our students here. Once we taught you, you're our students, you're our students forever. So whenever you have any question, regarding technology, right, regarding learning, regarding, deep learning, you know where to find us. Okay, you know where to find us. And I also want to thank you for our instructor, Shane, Richard, and Ying, right, for all your effort in terms of putting, this great camp together. I also had many sleepless nights, but I think we made it all the way to the end. When you think about, our students here, a lot of them came in without programming experience and they came out with this AI product. That is really, really impressive, right? When you think about, programming, we went through, like the whole quarters of Stanford introduction to like programming, in maybe a couple of days, right? And when I showed, a similar product to a professor at Stanford, and he was so impressed with what we can do. So I think we're special. I think I mean, it's not, I think I'm special. We are special. So thank you so much for, paying attention. Thank you for our students for being so awesome, like staying with us and learning with us. This is really a group team effort. So really, really thank you for your participation and your trust, to to us, for us to teach you knowledge and life. Yeah. So thank you. Yeah.
And I think I speak for everyone when I say thank you to Michael too for putting this all together. I mean, really, you were the driving force behind this.
Oh, thank you. Yeah. Okay. So with that, I want to end it. We are here for you, still. So, I know some of you want to drive, through, right, to more, like for the project, keep on doing that. We're going to support you for that. Also, we will invite you for future events, whether it's like guest speakers or, some seminars. Maybe, some of you mentioned about self-driving. We're probably going to pull a class together for self-driving as well for reinforcement learning. So that would be something that we probably, for sure, once we put that together, we're going to invite you. Okay. All right. Thank you so much. And I will see you around.
Yeah. Yep. Great job, guys.
Thank you. Bye-bye.
Thank you.
Bye-bye.
Thank you.
Bye-bye.
Thank you, Michael. Thank you, Shane.
Bye-bye.
Thank you, Michael. Thank you, Richard. Thank you, Shane.
Thank you, Michael.
Thank you, Michael. Thank you, Shane. Thank you, Richard.
Thank you, everyone.
Bye, guys. Bye, Randy. Good luck.
Congrats.
Good luck. Alex, good luck. Okay, I'm gonna